Hello everyone, my name is Yakubos Kolokasis, and today I'm going to talk about how Spark could exploit the large capacity of fast storage devices for efficient caching of intermediate results. This is joint work with Anastasios Papagiannis, Fivos Zakak, Soai Pakram, Christos Kousganitis, Polybios Pratikakis, and Angelos Bilas. Today, Spark supports a caching mechanism to store the result of an RTD. This mechanism is essential when an RTD is used across multiple Spark jobs. Caching avoids recomputation and reduces execution time, mainly for iterative analytics workloads. Today, Spark API supports different storage levels to cache RTDs. There is a storage level such as memory only that cache the RTDs on heap inside executor storage memory. While also you have the option for off-heap caching over a local storage device with the disk-only option. Also, Spark supports memory and disk storage level that you can combine both on-heap caching with off-heap caching. But the main question here is how much data do we need to cache? Well, as we observe, today the analytics datasets grow at a high rate. As we can see in the figure from a recent report by Seagate, today the global data accounts to be 50 zettabytes, and on 2025 is going to be 175 zettabytes. 3.5 times higher. So for this reason, a typical deployment of Spark uses roughly as much DRAM as the input dataset. But typically, the cache data is even larger than the input dataset. In order to estimate how much higher are the cache data compared to the input dataset, we ran some experiment using three well-known machine learning workloads in Spark: linear regression, logistic regression, and SVM, with a small dataset, which is 64 gigabytes. As we can see from the table, the cache RTTs are 3 times higher than the input dataset. So in-memory caching needs a lot of DRAM, but today the DRAM density is difficult to increase. On the other hand, we have the fast storage devices like NVMe SSDs that scales to terabytes per device and also are cheaper compared to DRAM. For this reason, Spark today uses fast storage devices for cache data, but at a high cost. Here in the top picture, we show how Spark today uses the fast storage devices. We show how memory and disk storage level works. We have the executor memory. That executor memory is divided into two logical spaces: execution memory and storage memory. We have the storage memory as an on-heap cache, and the rest RTTs that cannot fit in the storage memory are serialized and located in the disk. So we have some RTTs on heap, and when a new RTT is created and we want to cache it, then Spark, based on a least recently used policy, evicts some older blocks from storage memory and serialize them to the device. This operation happens on every iteration of the iterative workloads. We have to deserialize them, allocate them back, perform computation, and then again serialize them to the device. So this technique has a high serialization to serialization cost. Some related works use the fast storage devices as an extension of the DRAM. They try to extend the Java heap over the fast storage device. Here in the figure, as we show in the figure to the bottom, we have a very large heap over a fast storage device, and now we have execution memory and storage memory, a larger on-heap cache, so we can locate more RTDs on heap. But this technique introduce high garbage collection costs, because when the garbage collection is going to wake up and try to traverse this huge heap, it's going to spend a lot of time to reclaim the dead objects. And also, the cache entities in this situation are long-lived objects, so the garbage collection is going to waste a lot of time to reclaim a very small portion of the heap. So we have two worlds. The first approach is an on-heap cache that introduces no serialization but incurs high garbage collection costs. And on the other hand, we have off-heap caching that introduces low garbage collection costs but high serialization deserialization costs. Can we do some better? I mean, can we eliminate serialization and try to reduce the garbage collection cost? In order to answer this question, first take a look in an example of a Spark program. Here we have a Spark application. We load some dataset, we create some RDTs, then we persist these RDTs, and then we perform operation over these RDTs, and finally we persist. When we load the dataset and create the RDTs, then a lot of new objects are generated in the Java heap, as we show in the figure. When we select to persist some RDTs, then some of these RDTs are persisted. So we show in the Java heap these RDTs that are located in the on-heap cache in storage memory. And then we perform operations using these cache RDTs. During our operation, we have the interrupt of the garbage collection. So the garbage collector is going to clean some object and then create some other objects and then clean some object, then create some new object during the operation. So the garbage collector during persist and unpersist operation spends a lot of time to traverse this whole heap and reclaim a very small portion. Also, the cache RDTs are alive during persist and unpersist operation. Finally, when we do the unpersist operation, the cache RDTs can be reclaimed all together in the next garbage collection. So in our work, in our design, we treat the cache object differently. We have the Java objects that follow the generational hypothesis, that the hypothesis says that when a new object is created now, it's prone to die young. However, the cache data in Spark has a nomadic behavior because actually the Spark cache object has long lifetime because we use them across multiple Spark jobs. Also are intermittently accessed because we can create them, cache them now, and have a long interval without accessing them until we have an operation that will use these cache RDTs. And finally, these RDTs object that are consistent RDT has the same lifetime. So in our design, we place the cache object in a special heap. Next, we introduce a second JVM heap to locate the cache RDTs object that is a memory map over a fast storage device. So in our design, we have two heaps, an execution heap that remains as garbage collected heap, and we maintain this heap for execution purposes, while the second heap, the TeraCache heap, locates the cache RDTs and has two main benefits. It's not garbage collected because we use the semantic from Spark of persist and unpersist operation. And also, we eliminate serialization, deserialization of the cache RDTs object because we use the memory mapped IO. Here we show the design overview of TeraCache. As we said, we have the Spark executor, and the memory of the Spark executor by default is divided into two logical spaces, execution memory and storage memory. We exploit these benefits to have a JVM now that supports two different heaps. The JVM heap that is garbage collected, and we use it for the execution memory, and TeraCache, while it's the second heap that we use it for the storage memory. The JVM heap is fully located on DRAM, the DR1 part, while the second heap, the TeraCache, is memory mapped over NVMe SSD, and the rest part of the DRAM we use to locate the memory mappings of TeraCache. Today, the JVM is unaware of the cache operations that Spark made. As a result of that, the JVM handles the cache RTDs object as uniformly as all the other Java objects. So in our design, we make the JVM aware of the caching operation. As we show in the figure here, we have the Spark application that runs on top of the Spark runtime, and all of this runs on top of the JVM. And now our JVM supports two different heaps, the JVM heap and the TeraCache. When the Spark application performs a persist operation, then the Spark runtime stores these RTDs to storage memory. At this time, we notify the JVM to mark this RTDs object. In order to achieve this operation of the marking of this object, we add a new extra word in the JVM object headers, such as metadata, and we enable this word when the new object is created. As a result of that, we know which object needs to be transferred to TeraCache in the next full garbage collection. So, as we show in the example here, a new object is created in the JVM heap. Then we mark this object, and then we mark also the children of this object. And then in the next full GC, we move this object to TeraCache. Now, I'm going to discuss in the rest part of my talk about how we avoid the garbage collection in TeraCache and how we avoid serialization, deserialization. First, I'm going to explain how we avoid the garbage collection in TeraCache. In order to eliminate and avoid the garbage collection in TeraCache, we disallow the backward pointers from the TeraCache heap to the JVM heap. Let's see an example here, as shown in the figure. We have the JVM heap that has some object, and we have the TeraCache that locates some other object. If we have an object from the TeraCache heap that points to an object in the JVM heap, then we might have two bad scenarios. The first one is that the garbage collector is going to wake up and try to reclaim this heap. So it might reclaim this object, and then we will have a duckling pointer and our system will crash. The second scenario is the garbage collector move this object in another location in the JVM heap, so again we will have a duckling pointer. So in order to avoid the garbage collection in the TeraCache, we move the transitive closure of an object from the JVM heap to TeraCache, as a result to disallow backward pointers. Next, we allow forward pointers from the JVM heap to TeraCache because objects in TeraCache do not move, but we fence the garbage collector from following forward pointers into TeraCache because now TeraCache is located in a slower device, and we will have a performance overhead. But we said that in our analysis that the object that consists an RTD has the same lifetime. So we exploit this benefit, and objects that belong to the same RTD, which have similar lifetime, we select to locate them in the same region. For this reason, we select to have TeraCache. We organize TeraCache into regions, and every region contains similar lifetime objects. The size of each region could be dynamically. So having regions with objects with similar lifetime will give us the opportunity to reclaim entire region instead of individual object in each region. So in order to achieve the reclaim of entire regions instead of individual objects, we have to provide correct and bulk free. For this reason, we allow only pointers within regions between objects, but not pointers across two regions. So, as we show in the top figure, we have the JVM heap and the TeraCache. When we're going to move objects from the JVM heap to TeraCache, we identify that we have a pointer from the JVM heap to a certain region in the TeraCache. So these three objects were going to be moved in a new region in the TeraCache, and then we are going to merge these two regions into one. But how now we're going to reclaim entire regions, and how now we know which regions are active and which regions are inactive without automatically garbage collect in the TeraCache. In order to know which regions are alive and which regions are inactive, we keep a bitmap with live regions and track reachable regions from the JVM heap on every garbage collection. During the marking phase of the garbage collection, we identify, as we show in the second figure, we identify which regions are active. So the first region in this case is active, so we mark this bit in the bitmap array, and while the second region is not active. So at the end of the marking phase, we can reclaim the second region entirely by zero regions metadata without introducing any I/O to the device. Here, I'm going to show how we avoid the serialization deserialization. In order to avoid serialization deserialization, we use the memory mapped I/O. Memory mapped I/O allow us to have the same data format both on memory and the device. And we access the data on the device using load store instruction without explicit device I/O. Linux kernel today already supports required mechanism for memory mapped I/O, but in our design, we use the fastmap. It's an fastmap optimizes the scalability of Linux memory mapped I/O. If you need to read more about the fastmap, you can read the ATC paper. So, let's recapitulate the design of the TeraCache. We have the Spark executor, and the Spark executor memory is divided into two logical spaces: execution memory and storage memory. Now we have two separated heaps that share the same DRAM resource. The JVM heap that is fully located on DRAM, tier 1 part, while TeraCache is memory mapped over the fast storage device, and in the rest part of the DRAM, we locate the memory mappings of TeraCache. So, execution memory must reside in DRAM because produce a lot of short-lived data, so we need large tier 1 size, while we have iterative jobs that reuse cache data objects, so we need to have a large space for tier 2 to locate more memory mappings and reduce the access time of the TeraCache. So the problem here is how we are going to divide the DRAM resource between the JVM heap and the TeraCache. This approach can be statically or dynamically. Well, to answer this question, we ran some experiments using different configuration of tier 1 and tier 2. The x-axis in this plot shows the DR1 size over a total DRAM that is 32 gigabyte. And when we increase the DR1 size, the DR2 size decreases. In the y-axis, we show the execution time in minutes. Using in this experiment, we use the k-means and linear regression workloads. K-means job produce more short-lived data, so we have more minor garbage collections. So we need more space for DR1. For this reason, when we increase the DR1 size from 4 gigabytes to 8 gigabytes, the total execution time decreases by 3 times. On the other hand, linear regression jobs reuse more cache data objects, so we have more number of page faults. As a result, we need more space for DR2 to locate more memory mappings of TeraCache in DRAM. So when we increase the DR1 size from 8 gigabytes to 16 gigabytes in linear regression, the total execution time increases by 2 times. So the division of DRAM cannot be statically, but we need a dynamic resizing policy for DR1 and DR2 based on the number of page faults and the number of minor garbage collections. Here we show the implementation of TeraCache. We implement a prototype of TeraCache based on parallel GC of the JVM hotspot, and we place the new generation on DRAM and old generation over the fast storage device, and we explicitly disable the garbage collection in old generation in order to estimate the performance improvement when there is no garbage collection over the cache data. Currently we're working on the cache RDD reclamation mechanism and the dynamic division of DR1 and DR2. Now I'm going to show some graphs, and I'm going to show the performance improvement over the garbage collection overhead and serialization deserialization overhead. Here we show 4 machine learning workloads running in Spark: k-means, linear regression, logistic regression, and SVM in the x-axis. And in the y-axis, we show the execution time over the different machine learning workloads. Here we show 3 different configurations. The first bar in each cluster shows the performance when we use a swap heap that is swapped over a fast storage device using Linux kernel swap mechanism. So in this situation, we have a very large heap using a heap that is swapped over a fast storage device, and we use the memory-only storage level in Spark. But here, the main problem is that the garbage collection traverses also objects that are located in the NVMe device, and also the location of objects between the DRAM and the device is handled explicitly by the OS. The second bar in each cluster shows the performance when we use the memory and disk storage level in Spark, and the third bar in each cluster shows the performance of TeraCache. TeraCache improves performance by 25% on average and up to 37% in linear regression compared to memory and disk storage level. Also, TeraCache is better up to 2 times compared of having a swap heap that is located over a fast storage device using Linux kernel swap. In both situations, we eliminate serialization deserialization, and also we improve the garbage collection time because we avoid to traverse the cache RDD's objects. Also, here we show the garbage collection time in memory and disk storage level in the 4 workloads that we discussed before, and in TeraCache. The first bar in each cluster shows the garbage collection cost in memory and disk storage level, while the second bar shows the garbage collection cost in TeraCache. TeraCache reduces garbage collection time by up to 50% because avoid to traverse on every garbage collection cycle the cache RDD's objects. To conclude, in this work, we design and propose TeraCache, an efficient caching over fast storage devices. We observe that Spark incurs high overhead for caching RDDs over fast storage devices today, and we observe that Spark cache data has a nomadic behavior. Based on these two observations, we introduce TeraCache, which both reduces garbage collection time and eliminates serialization deserialization cost by using two separated heaps. From an early prototype implementation, we show that TeraCache could improve performance of Spark machine learning workloads by 25% on average. Currently, we are working on the full prototype. Thank you for your attention. I will be happy to answer your questions.